Welcome! In this video, we will finally begin discussing the free particle solutions of the Dirac equation. We are going to have to go through a derivation that's going to be a little bit tedious, but it's nothing out of the ordinary, so don't be too afraid. Now, we are going to use a procedure very similar to what we did in the case for Klein-Gordon, and in fact, it's going to be, well, basically the same beginning. Why? Because we know that the solutions to the Dirac equation also obey Klein-Gordon, right? We proved this a couple of videos ago. So for that reason, we can start off by taking our solutions to be some linear combination of plane waves. So they're going to be looking like that, very similar to what we used in the case for Klein-Gordon. So let's now plug this into the Dirac equation. Now, let's just remember, this is what the Dirac equation looks like, right? It's I gamma mu del mu minus m. We can sometimes use the slash notation here. It's perfectly valid to do so. Times our solution equals 0, right? And now we plug in what our solution actually is. Now, the spatial derivatives here will not act on u of p because it doesn't have a spatial component. So that means it's only going to act on this exponent here. So we are going to be left with I gamma mu p mu. And well, we have the minus I factor, which used to be in front, but you can move it around. It's just minus I. There's no issue there. And then we have this minus m and still u of p e to the minus I px equals 0. I just noticed I didn't put the 0 there. So now here we can quickly simplify the i's, right? So that's going to be minus 1 times a minus. So simply gamma mu p mu minus m. And again, we could use here the slash notation, but it doesn't matter. It's the same. And then we have u of p. And for this thing to be 0, either this entire thing is 0 or the exponent here is 0. And the exponent is not going to be 0. So we can just forget about it for now. All right, so this is what we have. And now the way to solve this is that we are going to now go to the rest frame of our solution. And then we're going to apply a boost to go back to the general case. So we're going to focus on the rest frame. And what this means is that our P is going to be, well, let's call it P0. And that is simply going to be the rest mass of the particle and 0, right? No momentum. From its point of view, it is not moving, right? So that's what we are doing. We are jumping on top of our particle. And from that point of view, it is not moving. And later, we'll apply a boost, right? Our famous lambda 1/2, which is the classic notation. And from that case, we are going to go back to the general situation. Okay, so in this situation now, we multiply what we have, right? The gamma mu times p mu. Keep in mind, the gamma mu's is simply going to be gamma 0, comma, the gamma i's, but it's going to be multiplied with m, comma 0. So the gamma i's will be multiplied by 0, so they're gone. So we're left with gamma 0 times m. All right, and then we have minus m. And well, u of p0 now. Now, what is gamma 0, right? Gamma 0 in our Weyl representation is 0, 1, 1, 0. Whoops, that's supposed to be a 0. There we go. And now we plug it in. So this would be 0, m, m, 0. Or we could factor the m outside. I think I'm going to factor it out. So there's an m here and an m here. So I'm just going to take it outside. So this is 0, 1, 1, 0 minus, and keep in mind, there is an implicit identity here, right? So this is just going to be 1, 0, 0, 1. Okay, so don't be confused. This is not just like a 1 by 1m. This is the mass times the identity. All right, I need one more parenthesis here. And then we have u p0 equal 0. All right, so from here, well, we just add this together. So we're going to have minus 1, 1, 1, minus 1 times u of p0 equal 0. And from here, we can find our solutions. So our solution here is simply going to be, so u of p0, we're going to have a normalization factor of the square root of m. This is here purely by convention, and we will very soon see why it is necessary. So we're going to keep it, and later we're going to see, oh, this is where it really comes in handy. So that's just there because it's useful later on. Then we have our actual solution. So that's going to be, well, we're going to be calling this chi and chi, right? And each one of these is going to be a spin state. So these chi's can be spin up or spin down, right? Which would be 1, 0 or 0, 1, right? So this actually has 4 dimensions here. It's 1, 0, 1, 0 or 0, 1, 0, 1, right? So this is our solution, and we plug it in here, and we can easily see it does, in fact, solve this, right? Minus 1 times this, plus 1 times this, 0. No issue. And the same thing here, it's always 0. So this is the solution. This is a quite important result. And now we have the solution for the rest frame. We want to go and apply a boost to it. Okay, so now we're going to apply the boost along the 3 direction. No particular reason why the 3 direction. It's just that something that apparently teachers like to use. So it's likely that yours will do it too. It doesn't really matter, along a direction. Okay, so first we're going to apply the boost to the energy momentum 4 vector. So we're going to have EP3. This is going to be equal to our rest mass, right? Just the rest mass, what we had in that case. And then now we have to actually apply the boost to it. So in this case, as we have seen previously when we were discussing these things, the boost is simply going to be the exponential of the rapidity. And now we have the matrix that defines the boost, which is going to be 0, 1, 1, 0 in our case. So from here, we need to do a little bit of algebraic manipulation, nothing really too crazy. But what we are going to do basically is that we are going to say, well, we know that e to the x can be written as a power series, right? What is the power series of e to the x? It's the infinite sum, right, from n equals 0 all the way to infinity of x to the n over n factorial. Well, what does this look like? Well, that's simply 1 plus x over, let's say this is 0 factorial, 1 factorial, then we have x squared over 2 factorial, plus x cubed over 3 factorial, x to the 4th over 4 factorial, and so on and so on. So in this case, let's say that this little matrix of ours is called A, right? Just because I don't want to have to write it down all the time. So in our case, we have e to the eta A. So this would be the infinite sum, n equals 0 to infinity of eta A to the n over n factorial. So this would be, again, well, in this case, it wouldn't really be 1, it would be the identity. So this would be just the identity in our current dimensions divided by 0 factorial plus. And then we have, instead of x, this is eta A divided by 1 factorial plus eta A squared divided by 2 factorial plus eta A cubed divided by 3 factorial. I'm going to do, I think, 2 more. So eta A to the 4th divided by 4 factorial. And finally, eta A to the 5th divided by 5 factorial. And of course, this goes on and on and on. And keep in mind, well, we are in a 2 by 2, right? A is 2 by 2, at least in blockwise. So this would be I2. Okay, so that's just a 2 by 2 identity there. All right, so now let's take a little bit of a look at our matrix A. So we know that A is 0, 1, 1, 0. So a squared is going to be the product of 0, 1, 1, 0. I like to write it up here, right? So 0, 1, 1, 0, just to make the product easier. So this is this times this, plus this times this. So we get 1, this times this times this, 0. Then we get another 0 and 1. So this is simply the identity 2 by 2. So that means that a cubed is going to be the identity times a, which is simply a. This means that a to the fourth is going to be a times a, right? So, and that's simply the identity 2 by 2. So what this says is that in general, we are going to have that a to the even number is going to be the identity, while a to the odd number is going to be a. So let's now apply it here. So eta a squared, this would be, well, eta squared, and then a squared is simply the identity 2 by 2. Eta a cubed, that is eta cubed, times a. Now to the fourth, we get eta to the fourth times the identity, and then we get eta to the fifth times a. And so on, and so on, and so on. So now let's group these things up. So let's factor by the identity and by a. So we're going to have the identity here, factor of. We have this, this, and this, and well, and then infinite terms, but I'm going to use those three to represent what's going on. So this would be, well, the identity over 0 factorial plus eta squared divided by 2 factorial plus eta to the fourth, sorry, I didn't mean to write that, over 4 factorial, and then we have a factor of this, this, and this. Maybe I should use a different color, so this, this, and this. So that would be eta over 1 factorial plus eta cubed over 3 factorial plus eta to the fifth over 5 factorial. And of course, well, in principle, maybe I should write this down, right? This is plus dot, 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 right? So we have infinite terms here. I'm just using these ones to represent what's going on. Okay, so what are those things? Let me just quickly remind you of, well, these two things. The hyperbolic cosine of x can be written as the infinite sum, n equals 0, to infinity of x to the 2n divided by 2n factorial. And that is precisely what we have over there. Meanwhile, this thing right here is going to be the hyperbolic sine of x, which can be written, right, as the infinite sum from 0 to infinity, x to the 2n plus 1 divided by factorial of 2n plus 1. And that's exactly what we have there, of course, with x being eta. So with that in mind, we can go back to the exponent here. So e eta a can be written as, this would be the identity, 2 by 2, right? The identity factor of the hyperbolic cosine of x, and then we have plus this thing right here, right? So plus the hyperbolic sine of, sorry, it's not x, it's eta, eta, and the hyperbolic sine of eta. And then we have a, so that. There we go. So that is what the exponent is equal to. So that's what we now want to plug back into our original expression. So this, we will now want to plug in where we left off. Let's see, where was it? We went way down. Let's see. So now let's write what the identity and a are, right? So the identity is, well, 1, 1, 0, 0. And it is multiplying the hyperbolic cosine of eta. I'm going to go step by step. And then we have a, which is 0, 1, 1, 0, times the hyperbolic sine of eta. And this is multiplied by m0. Now we can multiply inside. So here we get the hyperbolic cosine of eta, hyperbolic cosine of eta, and then we add with the hyperbolic sine of eta and the hyperbolic sine of eta. So I skipped a step there, but I hope it's all clear. m0. Okay. So now we can multiply through and we're going to get a nice little result. So E and P3, this is going to be, now we multiply. So this times this is going to be m cos eta, and then this times this is going to be m sinh eta, right? And well, that's our little result here. That's what we get for the transformation here. And this eta is basically the rapidity, as it is called, which is basically what is telling us how much we are boosting. And what we can see from here as well is that the energy is going to be m hyperbolic cosine of eta, while the momentum along which we are boosting, along the direction which we are boosting, is going to be m hyperbolic sine of eta. So that's our first little result. Okay, so now we want to do the same that we just did, but for our u of p. So let's remember the generators for our Lorentz transformations and for our boosts especially, which are going to be the following, what we have right here. So we are going to be in the case, of course, where I is equal to 3. We're going to go along the 3 direction. So in that case, we're going to have that our S03 is going to be minus I over 2 sigma 3, 0, 0 minus sigma 3. And our actual transformation itself is going to be the exponent of minus I over 2, and this little omega is going to be 0, 3, and S03. So, well, here we can actually plug this thing in, and we get that our transformation is, well, the exponent. We can call this right here, so we can call eta is going to be our omega 03 divided by 2, so that's the rapidity, right, as we mentioned before. So that's just so that our nomenclatures end up matching. So this would be minus I, then we have our eta, and now we plug in S03, which will give us another minus I over 2. And then we have our little sigma 3, 0, 0 minus sigma 3. And well, here we can do like some very, very simple simplifications. So this is exponent of the minuses cancel out once, but then we get another minus sign because of the i's, and we get a minus eta over 2 sigma 3, 0, 0 minus sigma 3. So what this means is that our u of p, right, this is what we get after we apply our boost on our rest frame. So our boost is this thing right there. So I'm gonna copy it. And then we have our UPO0, which is what we already found. So that is simply going to be m, or rather the square root of m. And then we have our chi. Now we're going to do the same procedure as before. So we're going to take a look at the exponent here. So this is going to be, remember, just like before, e to the x is going to be the infinite sum, right? N equals 0 to infinity of x to the n over n factorial, which means 1 plus x squared plus x cubed plus x to the fourth, etc. And we have all the factorials down here. So this is 1 factorial, 2 factorial, 3 factorial, 4 factorial, and so on and so forth. So again, in our case, we have e to the minus eta over 2. And let's call this matrix here B, just for simplicity. So that's going to be B. So again, this will be infinite sum, n equals 0 to infinity, of minus eta over 2 b to the n. And this is going to be over n factorial. So let's begin. Now, this would be, first, of course, we're going to get the identity. And then, well, what dimension is going to be the identity? It's going to be another little 2 by 2. Then we have this thing normal, right? So we're going to have minus eta over 2. And then we have this b and 1 factorial. Now we get that thing squared. So we get minus eta over 2 squared b squared divided by 2 factorial. Now we get it cubed. So we get minus eta over 2 cubed b cubed over 3 factorial. Now we get it to the 4th power. So we go for minus eta over 2 to the 4th b to the 4th divided by 4 factorial. And now we got this to the 5th. So minus eta over 5. Sorry. I mixed it up. So eta over 2, of course. Eta over 2 to the 5th b to the 5th divided by 5 factorial, and so on and so forth. Okay. So now let's look at our b, because b is sigma 3, 0, 0 minus sigma 3. But sigma 3 itself, right? So sigma 3 itself, what size is it? Oh, by the way, this is looking, so this is actually going to be the 4 identity, not the 2, sorry. Anyways, so our sigma 3 is 1, 0, 0 minus 1. So if we have b squared, so b squared, it would end up being, well, since it's diagonal, it's going to be the square of each one of the elements of the diagonal. So that's going to be sigma 3 squared, 0, 0. And then we get minus sigma 3 squared. So what is sigma 3 squared? Sigma 3 squared, I'm going to write that 3 a little bit better there. This thing, well, again, you square the elements to the diagonal, it's simply going to be the identity. So that means that b squared is going to be, well, the identity 4 by 4. So 1, 0, 0, 1, but you keep in mind, each one of these is actually the identity 2 by 2. So this is 0, 0, identity. So this is the lazy way of writing 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0. So these two things are the same. This is just the lazy way of writing it. So this 0 is actually the 2 by 2 0, and all of that is just 2 by 2. Okay, so given that, we now know that b cubed is going to be equal to b squared times b, so simply b to the 4th is going to be the 4 by 4 identity again. So what this means is that our b to the even power is going to be the 4 by 4 identity, and the odd powers are going to be b. Okay, knowing that, let's go back to this little expression. Okay, so here our b squared is going to be the identity. Our b cubed is going to be b. B to the 4th is going to be the identity. B to the 5th is simply b. Okay, now again, let's factor the identity and also b and group them together. So we are going to have that e to the minus eta over 2b is going to be equal to, so we have the ones where we factor out the identity, where we get, well, another case of the identity, plus. Then we have this one, so that would be minus eta over 2 squared divided by 2 factorial plus minus eta over 2 to the 4th divided by 4 factorial, and so on and so forth. So there we considered this and this and this. Now let's consider this and this and this. So in that case, we are now factoring out b, and we have b factor of minus eta over 2, well, divided by 1 factorial plus minus eta over 2 cubed divided by 3 factorial plus minus eta over 2 to the 5th divided by 5 factorial, and so on and so forth. So basically, what we are seeing is that just like before, this thing here is looking an awful lot like the hyperbolic sine of eta over 2 with a minus sign. And this is looking like the hyperbolic cosine of eta over 2 with a minus sign. So with that in mind, let's rewrite the exponential here. So e to the minus eta over 2 times b. This is going to be the 4/4 identity times the hyperbolic cosine of minus eta over 2. But the hyperbolic cosine is even, right? So that minus sign is completely irrelevant. So that's simply going to be eta over 2. And then we get plus b times the hyperbolic sine of minus eta over 2. But the hyperbolic sine is odd, right? It's an odd function. So that means we can take out the minus sign. So we can take this minus and put it over there. There we go. Now let's, well, we can either replace what I4 and b is here, or we can do it later. I think let's do it here this time. So let's replace the values of these things. So this would be 1, 0, or maybe let's try to be consistent. So I2, 0, I2. It is very common that you're going to see people just write 1 when they refer to like the identity in 2x2. But I guess it's better to be a bit more explicit, especially when people are first learning about this. So this is now hyperbolic cosine of eta over 2 minus, and b is sigma 3, 0, 0 minus sigma 3. And then we'll have the hyperbolic sine of eta over 2. Good. Now we can multiply through and put it all together. So this would be I2 hyperbolic cosine of eta over 2 minus sigma 3 hyperbolic sine of eta over 2, and then we get a 0 over there, a 0 over here, and now we get the same thing but with a plus, because we get minus minus. So this would be I2 hyperbolic cosine eta over 2 plus sigma 3 hyperbolic sine of eta over 2. Okay, so this is what the exponent is. Now, we could actually develop this a little bit further, but I want to do that when we plug it back into our original expression. So where did this whole thing come from? So this whole thing came from this, right? So we want what we have times the square root of m times our size. That's going to be equal to our u of p. So plug it back in. So this would be u of p is equal to this thing, which I'm not going to write again, so I will just quickly copy and paste it. All right, and this is now multiplied by the square root of m and our little size. Okay, so now let's work on this expression a little bit more. Now, what we're going to do is work with the cosines and sines, right, the hyperbolic ones, because we can't really combine them as they are right now. but they actually have a lot in common, because we know that the hyperbolic cosine of x is e to the x plus e to the minus x over 2, and we know that the hyperbolic sine of x is e to the x minus e to the minus x over 2. Okay, so with that in mind, we can, well, rewrite what we have over there. So we have u of p, this is going to be. All right, so let's breathe in deep and let's go in. So we have 2 by 2 identity. Now the hyperbolic cosine, that's going to be e to the eta over 2 plus e to the minus eta over 2 divided by 2 minus sigma 3, and this is now going to be e to the eta over 2, and then we get minus e to the minus eta over 2 divided by 2. We get a 0 over there, a 0 over there, and now just underneath all this, we get this term right there. So this would be I2 factor of hyperbolic cosine, so that would be the same thing we had up there. So e to the eta over 2 plus e to the minus eta over 2 divided by 2 minus sigma 3, or in this case it's plus sigma 3, sorry. And then we have the sine, so e to the eta over 2 minus e to the minus eta over 2 divided by 2. And well, that's this. And of course, we still have our expression here of square root of m chi. All right, there we go. So this is our beautiful u of p. So now we can factor some things out. So you see we have positive exponent, negative exponent, negative exponent, and the same thing down here, right? Positive, positive, negative, negative. So let's factor them and group them up together. So again, this is u of p. All right. And now we're going to have e to the eta over 2 factor of. And now we have I2. Now let's leave the factor of 1/2. Actually, now let's leave it inside for now. It's fine. So this is I2 and then minus sigma 3, and all of this is divided by 2. And then we have plus e to the minus eta over 2. And we have factor of I2 minus minus, so we get plus sigma 3 divided by 2. Okay, then we have, well, 0 over there, 0 over here, and we do the same thing down there. So we have e to the eta over 2 factor of the identity. And then we have, so that's identity plus sigma 3, all of this divided by 2, plus e to the minus eta over 2 factor of, in this case it's going to be I2 minus sigma 3 over 2. And again, don't forget about this square root of m and our little guys outside. All right. So there's a few things we can do now. So we can work with these expressions, right? So we know, we can simplify them. We know that I2 minus sigma 3 over 2, right? We can rewrite for and plug in what it actually is. So I2, well, that's easy. That is 1, 0, 0, 1. Sigma 3, that is, I think it is 1, 0, 0, minus 1. I'm going to double check because I did not go this far to screw it all up because I didn't bother checking. It is, let's see, 1, 0, 0, minus 1. Yes, so I was correct, thankfully. All right, so we can continue. And all of this divided by 2. So we get 1 minus 1, so that would be 0, 0, 0, and then 2. But we have to divide it by 2, so we end up getting 0, 0, 0, 1. Now, in the positive case, so I2 plus sigma 3 divided by 2, well, in that case, we're going to get that this is the one that cancels out, and we end up with a 1 on top, so this is 1, 0, 0, 0. Okay, so we have now simplified that, and we will plug it in a moment. There's just more that we can do. So actually, now, let's do it right now. Let's do it step by step. So we can now rewrite this as, well, now the square root of m goes inside, so we have square root of m e to the eta, and now this I2 minus sigma 3 thing, which we know is 0, 0, 0, 1. So 0, 0, 0, 1. Then we have plus square root of m e to the minus eta, 1, 0, 0, 0, right? I'm just plugging in what we have. A big 0 there, a big 0 here, and then we have m e to the eta inside of a square root. That's the positive one, which is 1, 0, 0, 0, plus, and then we have square root of m e to the minus eta times 0, 0, 0, 1. Okay, and of course, let's not forget about our little chi here, which, again, I never really knew how to draw it, so I'm sorry. Okay, now, let's take a closer look at square root of m e to the eta. So this thing right here, we can plug in what e is, and we get, so m factor of cosine or hyperbolic cosine of eta plus hyperbolic sine of eta. Right? This is because, as just a side comment, since the hyperbolic cosine of x is e to the x plus e to the minus x over 2, and the hyperbolic sine of x is e to the x minus e to the minus x over 2, we can add them together, right? So cos x plus sin x, and we get that the one with the minus in the exponent cancel out, and we get 2e to the x over 2, which is simply e to the x. So that's what I'm using here, just in case anyone forgot about that. And that means, right, this thing here means, actually maybe I'll write it down here. So this is square root of m hyperbolic cosine of eta plus m hyperbolic sine of eta. But now comes into play what we found earlier. So if we go up somewhere, my handwriting is slowly becoming bigger as we go further down the document. Anyways, so we found that E is m cos eta and P3 is m sin eta. So that means that what we just found down here, right, is simply E plus P3. So that's, a lot simpler than what we had. Now we can do the same, but for m e to the minus eta. So we get m cos eta, right? It is an even function, so the minus just doesn't matter, but it does matter in the sign. So we get a minus the hyperbolic sine of eta. So here we get m cos eta minus m sin eta inside of the square root. So here we get E minus P3. Okay, knowing all of this, we can now go back to that expression over there, to our U of P. So plug in. Okay, there it is. So now I copied it. I made it a bit smaller so that we can go to a more reasonable size. So then, as we saw, me to the eta inside of a square root is simply the square root of E plus P3. I think I'm going to zoom in further. Yeah, that way. And this thing here is square root of e to the minus p3. This thing here is with a positive, so e plus p3. And this thing here is with a negative, so that would be square root of e to the minus p3. So now let's multiply inside of this little thing. So here we have, let's combine everything in the upper left quadrant of or spot of the matrix. So this would be square root of e minus p3, 0, 0, square root of e plus p3. And down here, well, this is 0, sorry. So yeah, then we have 0, 0. And down here we have square root of e plus p3, 0, 0, square root of e minus p3. All right. And now, again, we still have our little chi's. And now, finally, we're going to multiply through with the chi's. So that means that we get u of p, this is going to be. So this is now this times that thing, so this times this means we get simply e minus, so basically our little matrix here, so 0, 0, e plus p3 times chi outside, and then underneath, right, we get this times this, which is simply going to be square root of e plus p3, 0, 0, square root of e minus p3 chi, and this thing. So, okay, we're making a lot of progress, and in principle, this is kind of almost done, but we can simplify it just a little bit more. Why? Because you may recall from, I think, a few videos back, we defined a 4-vector sigma and sigma bar. And what sigma was is simply the identity, comma, our sigma i's, right? So identity 2 by 2, I guess I should remain consistent with my notation then. This should be I2. And sigma bar was I2, comma, minus sigma I. So let's take a little bit of a look at something. If I have p, now thinking of the 4-vector p, dot sigma, what does this give us? This would be, so this would be basically e, comma, our p's, right, our pi's, dot, right, our sigmas, so I2, comma, sigma i's. Now do keep in mind, the metric that we're using has a minus sign in the spatial part. So that means that by doing this, we get e times I2 minus p dot or pi sigma I. Now, of course, in our case, p and sigma are only in the 3 directions, so we only get p3 sigma 3. All right. Now, what does this thing look like? This would be e 0, 0, e minus, what is sigma 3? Sigma 3 is, as we saw before, 1, 0, 0, minus 1. So multiplying by the momentum, or p3, we get p3, 0, 0, minus p3. So we put all that together and we get e minus p3, 0, 0, e plus p3. And now we can take the square root, because this is p dot sigma, and we can take the square root of p dot sigma, and the square root of a matrix is the square root of its eigenvalues. And since this is a diagonal matrix, the eigenvalues are the elements of the diagonal. So for that reason, this thing is simply square root of e minus p3, 0, 0, and square root of e plus p3. And we can already see that this thing is exactly what we have in the upper half. All right, so that's one way to write this. So what we are now going to do is do the same thing, but now with p dot sigma bar. The only difference is that now there's going to be a minus sign over there. So that means that now we have E dot I2 plus P3 dot sigma 3. So that means that when we do all this, the only difference is that we get E plus P3 0 0 E minus P3. So now we can take the square root. So that's square root, right? P dot sigma bar. This is going to be the square root of E plus P3 0 0 E minus P3. And there we go. So now we can plug all of this. So plug this back in. So we get U of P, right? We look at this. The upper part is what we found first. So that would be square root of P dot sigma times our little chi. And the lower part is P dot sigma bar times chi. And that is the most compact way to write down these solutions. So there we go. Okay, so these are the solutions. And as we mentioned, it is very useful to go for our chi's to be the eigenstate of the sigma 3s. And well, that basically means 1, 0 and 0, 1. So as I said, it's going to be the two cases for the spin up and spin down. Even though talking about spin up and down it's maybe a little bit early for that, but that's going to be our two cases. So we can go, for example, right, in this case, for our U of P, let me move this down, to be, in this case, well, I guess we would have the square root of E minus P3, 1, 0, E plus P3, right? This is in a spin up situation. And now we can apply a large boost to it, for example, large boost. And by large boost, I guess I'm missing an O here. By large boost, what we mean is that our momentum is going to be way, way, way larger than our mass, right? So basically than the rest energy here of our particle. So for that reason, what we're going to have here is that the energy is basically going to be purely because of the momentum. So that means that we can approximate our solution here to, this is going to be 0. So 0, this is going to be square root of 2e, and then we still have this 1, 0. So we can then write this as square root of 2e, and then 0, 1, 0. Right, so that's what we can do for a large boost in the case of spin up. In the case that we have a large boost for spin down, well, it's going to be very similar. So in this case, we're going to have E plus P3, 0, 1, E minus P3, 0, 1. We now apply the large boost. And again, this thing is going to be 0, right? So we're going to get square root of 2e, which is coming from the term on top. So we have 0, 1, 0. Right, so that's just a nice little thing to think about, especially since those two solutions that we have now seen are also going to be the eigenstates of the helicity operator. Right, so the helicity operator is what we're going to define as P dot here, the direction of P times S, which is simply 1/2 of our Pi, sigma I 0, 0, sigma I. And now it's very important to note, if our particle has a helicity of plus 1/2, we are going to say it is right-handed, right? Right-handed. And if the helicity is minus 1/2, right? If the eigenvalue is minus 1/2, then we say it is left-handed. And this, by the way, is why we chose the names of psi L and psi R for our Weyl spinners a couple of videos back. The solutions of the Weyl equation back then have very definite helicities, right? One is left-handed, one is right-handed, and that's why we chose that name back then, even though we didn't really know what was going on. But now we know. So what we still need to talk about is some normalization conditions for these solutions and some very important identities that we will see very soon. So to normalize our solutions and ensure that they are still Lorentz invariant, this is going to be similar to what we did some time ago in the Klein-Gordon situation. We're going to have U bar U define the normalization condition. So U bar U is going to be 2m chi dagger chi. All right, and here it's going to be very important, of course, that our chi dagger chi has to be normalized to be 1, and U bar, just to make sure that we are clear, is going to be U dagger gamma 0. All right, so those are some very important definitions. All right, so let's start summarizing our results. We know that the solutions of the Dirac equation can be written as linear combinations, so our psi of x, they're going to be a linear combination of plane waves, right? And this is what we did for the case with positive frequency. We saw that we have two linearly independent solutions, right? Now we're going to have the S here so that I can denote the spin state, whether it is up or down, right? Whether our chi is 1, 0 or 0, 1. So we saw that this is going to be square root of p dot sigma, square root of p dot sigma bar, and then we get our chi, and of course they need to have the S so that we know if it is 1, 0 or 0, 1. And well, we can write it as 1 or 2, right? Which one it is. Now, the normalization condition we can write in general terms, and this may look confusing, but it's important that we get used to it, as U bar R of P, right? US of P. So basically R and S are denoting the spin states. Which spin state is it? Like when you have IJ mu nu, we just have R and S. So this can be calculated by just literally plugging this in. We know what P dot sigma is, we can do the calculation, and we also know that if we multiply our, let's say, a chi dagger R and chi S, these are going to be delta RS, right? They are 1 if they are the same and 0 if not. Why? Well, because this is going to be, for example, let's say that they are both 1, 0, then you get 1, 0, 1, 0, which is going to be 1. And if they are different, then you have 1, 0 times 0, 1, for example, which is going to be 0. If you flip it around, 0, 1, 1, 0, also 0. So that is how we find this thing. So this is going to be simply 2m times delta RS, right? 2m coming simply from the multiplication of these things. You are going to end up having energy minus P3. In the other one, you have energy plus P3. You can put them together and just quickly define that or find that. And then we have another important, so these are very important identities, by the way. So this is very important. If there's like one takeaway, it's probably going to be this, because we're going to have to, we're going to use it a lot when doing the whole quantization thing. So these are the properties of the solutions, which we are going to be using over and over and over again. So another important one is going to be UR dagger, right, of P, US of P. So very similar, but this time no bar. Keep in mind, the bar means there's going to be an additional gamma 0 in between, right? So in this case, we're going to have 2 EP delta RS. So those are two very important ones to know. So let me just give you a quick pointer as to where this comes from. So in this case, UR dagger, right? We know what this thing is. So this would be, so chi R dagger square root of P dot sigma, comma, chi R dagger square root of p dot sigma bar. And now we multiply this by the square root of p dot sigma chi s, square root of p dot sigma bar chi s. And well, now we multiply. So this would be, let's see. So chi r dagger, and then we have p dot sigma, p dot sigma. So the square root goes away. So we get p dot sigma. And then we have chi s plus chi r dagger p dot sigma bar chi s. We can now factor our chi's to the sides. So we can write this. This is equal to chi r dagger p dot sigma. What is p dot sigma? Well, p dot sigma is E minus p dot, in this case, p3 sigma 3, but in general, it's p dot sigma the i's. And then we have plus E plus p3 sigma 3. I guess we should denote the e's as EP so that we are consistent. Chi s. So the p's cancel out and we end up with 2 EP chi RT and chi S. So that's where it comes from. So that's just to give you a rough idea. And yeah. So similarly, you can find each one of these. As you can see, there's nothing too crazy about it. Some involve some extra steps. Sometimes you have like the gamma matrix in there or not. But yeah, it's the same thing. Okay, so these are 2 very important properties to know. Now we want to do the exact same thing that we just did, but for the negative frequency solutions. So basically what we had was, right, we had psi equals e to, sorry, I'm missing the up. So we had u of p e to the minus I px, right? So this was for the positive frequency solutions. But now we want to go for the negative frequency. So this time we're going to have p less than 0. And now let's, instead of u, call it v and work from there. Now to make things easier, what we're going to do is say, all right, p is greater than 0, but we switch the sign in the exponential, right? So we didn't really do anything. We just basically took the sign from p less than 0 and put it into the exponent, making it positive. So that way, it is going to be very similar to what we did before. So now we plug this into the Dirac equation, right? I gamma mu del mu minus m v of p e to the I px is equal to 0. And we take the spatial derivative, which is going to give us I gamma mu I p mu minus m v of p. This thing is not really the one that makes the expression be 0, so we get rid of it. And now we get a minus here, so we get minus gamma mu p mu minus m vp equals 0. And we can now multiply everything by a minus 1, so we get gamma mu p mu plus m vp equals 0. So this is what we have to work with now, and we go for the exact same thing as before. And notice the only difference is that before we had a minus here. So that minus is going to be the only difference, which is why we can skip through a lot. So I'm just going to show you how this starts and then walk you through the differences. So again, if we go to the rest frame, right, we have that our p mu is going to simply be mass comma 0. So for that reason, we get gamma 0 m plus m vp equals 0. So we can again write this as, this would be 0 m m0 plus m0, 0, m, keeping in mind there's like an invisible identity next to that m, v of p equals 0. So this is simply going to be m, 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 vp equals 0. So basically m times 1, 1, 1, 1, vp is equal to 0. So again, basically the same as before, but we just had a couple minus signs inside. So this means that our solution, v of p, is going to be just like before, square root of m, but now, well, first of all, we can't say chi anymore, so let's call it eta or something, I don't know, eta, eta. But now for this to be a solution, we need a minus sign in here. So we put a minus sign in here. And that's it. That is the only difference. So now, with this, we have to go through the entire calculation. If you want, you can do it again. But it's actually not necessary. Because take a look at this. Where the only difference is in the state itself, right? There is a minus sign in here, basically. So the entire calculation that we did here, and all of this is not affected. The only place when there is a difference is when we end up multiplying and putting this thing in here. So we can just continue. So you can see here, it's still the same. So there it is. The only difference comes in this final step. Because in our case, we have here eta minus eta. So far, everything has been the same. So when we multiply in, right, this is now going to be for our v's. So for our v and v, we are going to have eta and minus eta. That's the difference. Everything else is the same. This entire thing here, this is the same as well. Because our difference is here, is that this thing is now eta, and this thing is now minus eta. So in fact, that lets us see what our solution is. Our v of p is going to be square root p dot sigma eta minus p dot sigma bar eta. That's the only difference. And I'm gonna then go back here so that when I upload my notes, you guys don't get super confused, but I'll fix that later. All right, so that's the only difference. This is going to be our solution. All right, so we found that our solution is going to be this. And again, these etas are going to be either up or down, right? We have those two possibilities. But it's going to be very important that these etas now are going to be orthogonal to the chi's that we found before. So in general, we're going to be writing this vs of p, right? This is going to be just like before, p dot sigma minus square root of p dot sigma bar. And now these etas have this little s to denote the spin state that they are in. And there's also going to be some very important identities that you need to know. So the normalization factor is going to be the same as before, basically, up to a little minus sign, again, because of this. So we don't have that little minus sign. The only impact is that it adds a minus sign there. Similarly, when we now have this little dagger here, well, in this case, it's no longer going to have the minus sign. It's simply going to be 2EP. Maybe if it's really necessary, I can make a video going through each one of these identities, but I think that hopefully with what I explained before, you can get to it simply enough. So as I was saying, these quantities are going to be orthogonal to each other. So u bar of r and vs of p is going to be the same as v bar of r, us of p, and that's going to be 0. So that's also very important, okay? But not every time they are together, it's going to be 0. What there is also is ur dagger of p, vs of p, and that is not 0, right? And the same thing happens with vr dagger of p and us of p. So be careful about that, okay? So when you got the dagger, the bars, it's 0. But just with the daggers, not necessarily. Then we have UR dagger. So there is this one exception, right? So if we have the expression that we had up there, but with opposite momentum, then we do have 0. Okay, so that is one case where you do get 0, but it's not true generally. So that's very important. So these are the solutions to the Klein-Gordon equation. So what matters most is that you know this, right? You should know this. You should know also the expression for U, which is, well, the same without the minus sign and with a different name for the states, right? So this over there, you should also know how they are normalized, or at least have it written down somewhere, and know which combinations are 0, right? That's what you should know from all of this. The derivation itself, you should have gone through it once in your life. Now you did it. Congratulations. No need for it anymore. So yeah, I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment, and subscribe. And maybe consider checking out my Discord, the Discord server where we can share things with each other. We can talk about these things. You can find people who want to learn this as well. The link is in the description. You can also join my Twitch, twitch.tv/tkanik. We're going to be streaming every now and then, just talking about things not really physics related, but still. And if there's a particular topic that you would like me to cover, you can go to ablebees.com/team/Nick Heumann University and either start or support a petition, which is a great incentive to get me to do videos that you want to see. And if you really like the content, why not joining my Patreon, where I also upload all of the notes from the recent videos and for future ones, so that you can access those. So yeah, thank you very much for watching, and I'll see you in another video.